Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing covalent character in ionic bond. The contents of this module are introduction, polarization, polarizability, polarizing power of ions, prediction of covalent character based on Fajan's rules, ionic character of covalent bond, Hannay-Smith equation, and problems based on these concepts. First of all, introduction. The concept of covalent character in ionic bond arises from the fact that no bond is purely ionic. That means every ionic bond has some covalent character and every covalent bond has some ionic character. The concept of covalent character in ionic bond arises from the knowledge that no bond is purely ionic. Even in compounds typically classified as ionic, there is often some degree of electron sharing between the ions and it leading to partial covalent character. The blending of ionic and covalent characteristics is primarily due to the polarization effect. Greater the polarization, more will be the covalent character. Lesser the polarization, more ionic will be the character. So, polarization is proportional to covalent character. Polarization is inversely proportional to ionic character. Now, what is meant by the term polarization? Polarization refers to the distortion of the electron cloud of an anion, that is a negatively charged ion, by a cation, that is positively charged ion. This means that when a positive charge ion is placed near to an anion, there occur a distortion in the electron density of the anion. That is, the electron density surrounded the anion move towards the cation. That distortion in electron density of an anion in the presence of a cation is called polarization. This polarization effect directly proportional to the covalent character. The picture illustrates the polarization. The left hand side represents a positive charge ion or a cation, and the ion in blue color represents that of an anion. In the presence of this cation, the uniformly distributed electron density around the anion tends to move towards the cation. That distortion in electron density of an anion under the influence of a cation is termed as the polarization. Now, when a cation approaches an anion, the positive charge of the cation attracts the electron cloud of the anion, pulling it towards itself. This picture more clearly depicts the polarization of an anion in the presence of a cation. This green colored body represents the cation or positive charge ion, and the magenta colored body represents that of anion. In the absence of the positive ion, the electron cloud is uniformly distributed around the anion. However, in the presence of the cation, electron density of the anion is moving towards the positively charged cation. So, there is a distortion in the electron density of the anion in the presence of the cation. This is clearly depicts the polarization. This polarization leads to a shift in electron density affecting the bond's nature. Higher polarization leads to more covalent character as electrons are shared rather than completely transferred. It should be noted that a covalent bond is formed by the mutual sharing of electron. However, if there occurs some complete transfer of electron, that may lead to the formation of an ionic compound. Higher polarization leads to sharing of the electrons, that is, higher the polarization, more will be the covalent character. If the polarization is low, that is lower polarization, lower polarization maintains ionic character due to minimal electron sharing. That is, lower polarization implies minimum electron sharing and higher polarization implies maximum electron sharing. This picture represents the undistorted isolated anion, that is in the topmost row. In the second row, you can see the presence of a positive ion also. There occur the beginning of the polarization, and the last row represents the polarization of the anion that occurred in the presence of a cation, that is positively charged ion. So, the last part represents the polarized anion. Higher the polarization, higher will be the covalent character. Now, high polarization leads to high covalent character, while low polarization maintains the ionic nature of the bond. This can be exemplified by taking aluminum chloride. In aluminum chloride, the Al3 plus cation has high charge density, which distort the Cl minus anion's electron cloud, giving the bond more covalent than NaCl. This example implies that aluminum chloride has more covalent character than in NaCl. So, we can simply say that in NaCl there is maximum ionic character because there is minimal polarization, and in aluminum chloride, aluminum 3 plus polarizes Cl minus ions more, and hence there is more covalent character in aluminum chloride. Now, we are discussing another important term, that is nothing but polarizability. What is meant by the term polarizability? Polarizability is the ability of a negative ion to undergo polarization. We can enter into more details of the concept polarizability. Polarizability is the tendency of an anion to have its electron cloud distorted by a cation. You know the fact that generally anions will undergo polarization. The ability of such an anion to undergo polarization is called polarizability. It is influenced by several factors. The polarizability of an anion is influenced by several factors such as size of the anion, charge on the anion, electronic configuration, etc. Now we are discussing more about the factors influencing polarizability. First of all, size of the anion. The question arises is how size influence polarizability of an anion. The answer is here. Larger anions have a more diffuse electron cloud, making them more easily polarizable. That is, higher the size of the anion, its polarizability will be high. Moving on to an example, that is I minus. I minus is a bigger sized anion, which is bigger in size when compared with the Cl minus, Br minus and even F minus. That is, for the sake of convenience, we are taking two ions for comparison, that is I minus and F minus. So, it is very well clear that I minus is biggest in size and F minus is smallest in size among that anion radicals of halogen. So, the second factor that influence polarizability of the anion is charge on the anion. Higher the negative charge, there will be high polarizability. Higher negative charge increases electron density, making that anion more polarizable. So, if the charge is high, the rate of polarization is high, the rate of polarization of an anion is high, which implies that high charged anions are associated with high polarizability. This is an example. S2 minus is more polarizable than Cl minus. Or in another way, we can say that S2 minus is having high polarizability compared to Cl minus. This is because in S2 minus there is 2 negative charge and in Cl minus there is only unit negative charge. And moving on to the third factor, that is electronic configuration. How electronic configuration of the anion affects the polarizability? The answer is here. Anions with noble gas configuration, that is fully filled orbitals, are less polarizable than those with the pseudo noble gas configuration. Pseudo means wrong noble gas configuration, that is those with incomplete d shell. So, anions with perfect noble gas configuration is less polarizable compared with the other anions with the pseudo-noble gas configuration. Now, I minus is a large sized anion which is more polarizable than F minus due to small size, leading to greater covalent character in LiI compared to LiF. We are taking two substances, that is lithium iodide and lithium fluoride, for the comparison of their covalent character. In lithium iodide, the central anion I minus is very large in size, which is more polarizable. Higher the polarizable nature, higher will be the polarizability, higher will be the polarization, higher the polarization, more covalent will be the character. So, here in these two examples, LiF and LiCl, the LiF and LiI, the cations being the same but anions are different. So, you have to explain the covalent character based on the size and polarizability of the anion. I minus is big in size, it is associated with the high polarizability compared to F minus. So, it is very well clear that lithium iodide is more covalent than lithium fluoride. Now, we are discussing another important parameter, that is nothing but polarizing power of ions. What is meant by polarizing power? Polarizing power refers to the ability of a cation to distort the electron cloud of an anion. You know the fact that anions will undergo polarization only in the presence of a cation. So, the polarizing power is intended to describe the cation. Polarizing power is mentioned for cations. Polarizing power of a cation refers to the ability of that ion to distort the electron density or electron cloud of an anion. Several factors affect the polarizing power of cations. Now, let us go through what are such factors. The factors that influence polarizing power of cations are: number one, size of the cation. Smaller cations have higher charge density, leading to greater attraction of the anion's electrons. Now, what do you mean by the term charge density? Charge divided by volume. Bigger sized cations have lower charge density, but small sized cations have high charge density. Higher the charge density, it can enable strong polarization. That is, charge density is directly proportional to polarizing power. Size is inversely proportional to charge density. So, size is inversely proportional to polarizing power of cation. So, smaller sized cations have higher charge density and hence high polarizing power. Now, let us take Li plus and Cs plus for comparison. Li plus is smaller in size with only unit positive charge. In that group, Cs plus is biggest cation with only unit positive charge. So, from the above points, it is very well clear that Li plus is have high charge density and can have more polarizing power compared with the Cs plus. Moving on to the second factor that influences the polarizing power of a cation, that is nothing but charge of the cation. Higher charge increases attraction towards the anion or strong attraction towards the anion. For example, aluminum 3 plus has more polarizing power compared with Na plus. Here aluminum 3 plus is associated with high charge of 3 plus, and in the case of Na plus there is only unit positive charge only. So, Al3 plus is associated with high polarizing power when compared with Na plus. Next factor is nothing but electronic configuration of the cation. Now, the question arises, how electronic configuration of the cation influences its polarizing power. Cations with pseudo-noble gas configuration, that is wrong noble gas configuration, or associated with incomplete d subshells, exhibit higher polarizing power. For example, zinc 2 plus is a cation with a pseudo-noble gas configuration, has high polarizing power than Mg2 plus. Mg2 plus is a cation with the perfect noble gas configuration. Mg2 plus is having only 10 electron, which resembles the electronic configuration of the neon. So, Mg2 plus is having correct perfect noble gas configuration. At the same time, zinc 2 plus is associated with the pseudo noble gas configuration. So, it is having polarizing power different from that of normal or normal cations having noble gas configuration. Now, polarizing power can be illustrated by taking an example. You have to consider aluminum 3 plus in aluminum chloride and sodium plus in sodium chloride. It is very well clear that aluminum 3 plus has greater polarizing power than Na plus, making aluminum chloride more covalent than NaCl. This is because higher the polarizing power of the ions, higher will be the rate of polarization, higher will be the rate of polarization, higher will be the covalent character. So, in aluminum chloride, there is more covalent character compared with prediction of covalent character in ionic compounds. For this, we resort a set of rules that is nothing but Fajan's rules. We are now entering into details of the Fajan's rules and its applicability in the prediction of covalent character of ionic compounds or an ionic bond. Partial covalent character of ionic compounds is the first part of this discussion. Ionic compounds are not 100% ionic. Many exhibit partial covalent character. And what is the reason for such a partial covalent character? The answer is polarization of the ions. Higher the polarization, higher will be the covalent character. So, ionic compounds have some covalent character, and that covalent character is due to the polarization. The degree of covalent character in an ionic compound depends on a set of rules called Fajan's rules. These Fajan's rules describe polarization and covalent character. Now, Fajan's rules. The statements of the Fajan's rules can be illustrated in 3 to 4 points, and the first point is a small positive ion favors covalency. The second postulate of Fajan's rule is a large negative ion favors covalency. Third point, high charge of either sign favor covalency. That means high positive charge or high negative charge implies or favors covalency. And the last statement is this: polarization and hence covalency is favored if the positive ion does not have a noble gas configuration. Being very important role in predicting the covalent character of an ionic compound or an ionic bond, these 4 rules are highly relevant and most significant. So, on a consolidation you can say just like this: small cation, large anion, high charge of either sign and high polarization are various factors that govern polarizability of the polarizability and hence covalent character of an ionic compound. So, these 4 points illustrate covalent nature. All these support covalent nature or covalency of an ionic compound. Now, based on Fajan's rules, it is possible to compare the covalency of some ionic compounds. For example, if you are provided with some ionic compounds like NaCl, magnesium chloride, aluminum chloride, etc., it is possible to compare the covalent character as well as ionic character based on these Fajan's rules. Now, let us take some compounds as examples. For instance, we are taking the alkali metal, sodium metal and halogen compounds, that is sodium chloride, sodium fluoride, sodium iodide, etc. Here you are having 4 compounds and their increasing covalent character is in the order NaI greater than, NaBr greater than, NaCl greater than NaF. From this arrangement, it is very well clear that sodium iodide is associated with very high covalent character and sodium fluoride is associated with very low covalent character. That is, highest ionic character is associated with sodium fluoride. Highest covalent character is associated with the sodium iodide. Covalent character and ionic character are mutually opposite to each other. High polarization leads to covalent character, low polarization leads to ionic character. So it is very well clear, NaI is more covalent and NaF is more ionic. MgCl2 has greater covalent character compared with NaCl. There are so many reasons. MgCl2 contain Mg2+, that is a high charged cation with an oblique configuration. So MgCl2 magnesium 2 plus cation is having high polarizing power when compared with the Na plus in NaCl. So higher polarization is affected in MgCl2 and it is associated with the greater covalent character compared with the sodium chloride. Now ionic character in covalent bond. We are talking in an opposite fashion. The first part we discussed is covalent character in ionic compound. Now we are discussing in an exact opposite way, that is ionic character in covalent bond. So it is very well clear that no covalent bond is 100% covalent, no ionic bond is 100% ionic. In ionic bond there is few amount of covalent character also and vice versa. Now we are focusing on ionic character in covalent bonds. Covalent bonds involve the sharing of electrons between the atoms. However, if two atoms have different electronegativities, the sharing of electrons is unequal, which may lead to partial ionic character of the bond. When a covalent bond forms between two atoms with different electronegativities, the bond exhibits polar covalent behavior with the characteristics of both covalent and ionic bond. So, if there is a covalent bond between hydrogen and chlorine, there is considerable electronegativity difference between hydrogen and chlorine, so that HCl covalent bond is not 100% covalent, but it is a polar covalent bond. A polar covalent bond means which is associated with some ionic character also. So, such kind of covalent bonds have ionic as well as covalent character. Greater the electronegativity difference, greater will be the ionic character. That means greater electronegativity difference leads to greater ionic character. Higher the electronegativity difference, there is a chance for complete transfer of electron from one atom to other, and that may lead to the generation of oppositely charged ions, and hence ionic character will be more. So, higher the electronegativity difference, higher will be the ionic character. Now we are discussing the relation between the quantitative relation between electronegativity difference and ionic character. Ionic character refers to the extent to which a bond behaves like an ionic bond rather than a covalent bond. As the electronegativity difference, which is abbreviated as delta chi, which is the electronegativity difference between participating atoms in a bond, as delta chi increases, the ionic character of the bond also increases. For example, HF has higher ionic character than HCl because delta X between hydrogen and fluorine is larger. That is, in HF, fluorine is the most electronegative atom, and hence the electronegativity difference between hydrogen and fluorine in HF, delta chi, is very high compared with the electronegativity difference between hydrogen and chlorine in HCl. That leads to the conclusion that HF molecule is associated with high ionic character than HCl. Now, ionic character can be estimated using an equation. This is a quantification of electronegativity difference and ionic character. The equation relates percentage of ionic character with the delta chi. Delta chi is simply the electronegativity difference. Now, the equation is percentage of ionic character is equal to 1 minus e raised to minus 0.25 delta chi square multiplied with the 100. So, left hand side represents ionic character or percentage of ionic character, and right hand side include electronegativity difference between the participating atom as an exponent. This equation is known as Pauling's equation for estimating ionic character. So, the Pauling's equation, which is shown here, clearly depicts the relation between electronegativity difference and the percentage of ionic character. As delta chi, that is electronegativity difference, increases, the percentage of ionic character also increases. So, you can simply say that percentage of ionic character directly related to electronegativity difference between the participating atoms in a bond. Now, examples of ionic character based on electronegativity difference. We can illustrate this concept, electronegativity difference and its relation with the ionic character by taking some example. In the first column, there are some molecules which are connected by bonds. The molecules are H2, HCl, NaCl, MgO. Yes, in all these molecules there are bonds also. In H2 there is a hydrogen-hydrogen bond, in Cl2 there is a chlorine-chlorine bond, and so on. In the second column there is electronegativity difference between the participating atoms. The last column represents the approximate percentage of ionic character. It is very well clear that for hydrogen molecule, the electronegativity difference between the participating atom is equal to 0 since the atoms are same and the percentage of ionic character can be taken as 0. For HCl molecule, the electronegativity difference is equal to 0.5. Based on the Pauling equation, it is possible to assess the percentage of ionic character nearly equal to 18%. For NaCl, electronegativity difference is 2.1, which is greater than that in HCl. So, ultimately lead to higher percentage of ionic character. So, in NaCl, the percentage of ionic character is 63%. Finally, moving on to magnesium oxide. Here, the electronegativity difference between magnesium and oxygen is equal to 3.5, and which is the highest electronegativity difference among all the compounds given here. And that high electronegativity difference enabled nearly 90% ionic character to MgO molecule. So, electronegativity difference is directly correlated to ionic character, and you can evaluate percentage of ionic character from electronegativity difference using an equation that is nothing but the Pauling equation. Now, we are discussing another important equation, that is Hannay-Smith equation. Dipole moment can be used to assess the percentage of ionic character. In the previous slides, we discussed the application of electronegativity difference in predicting the ionic character. Now, it is also possible to elucidate the percentage of ionic character based on dipole moments, or we can say that dipole moment can be used to assess the percentage of ionic character. The percentage of ionic character is calculated by comparing observed dipole moment to the dipole moment if the bond were 100% ionic using an equation that is known as the Hannay-Smith equation. The Hannay-Smith equation is shown here. The left hand side of that equation is similar to Pauling equation, that is nothing but the percentage of ionic character. Percentage of ionic character is equal to mu observed divided by mu ionic multiplied by 100. Now, what is meant by mu observed? Mu observed means the experimental or measured dipole moment of the molecule. What is meant by mu ionic? This is called the theoretical dipole moment, and for calculating the theoretical dipole moment, we are assuming complete transfer of the electron, or assuming full charge transfer or full electron transfer. So, if you are knowing mu observed and mu ionic, it is possible to evaluate the percentage of ionic character. So, this equation, percentage of ionic character equal to mu observed divided by mu ionic multiplied with 100 is called the Hannay-Smith equation, which predicts the percentage of ionic character based on dipole moment measurements. Now, we are going to illustrate the Hannay-Smith equation using a specific example. If the observed dipole moment of HCl is 1.08 dBi and the theoretical value is 1.28 dBi, then what will be the percentage of ionic character of HCl molecule? Percentage of ionic character can be calculated by using the expression percentage of ionic character equal to mu observed divided by mu ionic multiplied with 100. So, in the case of HCl molecule, it is clear that the observed dipole moment is 1.08, and if it is assuming complete transfer of electron, that is in HCl, if H exists as H plus and Cl exists as Cl minus, then there is a theoretical dipole moment. That value is already given, it is equal to 1.28. So, the percentage of ionic character of the molecule equal to 1.08 divided by 1.28 multiplied with 100, that is equal to 84.4%. So, by knowing the observed dipole moment and the dipole moment for a 100% ionic molecule or a theoretical dipole moment, it is possible to evaluate the percentage of ionic character. Now, we are discussing some problems based on the concept we learned. This is the first problem. Arrange sodium chloride, sodium bromide, sodium iodide and sodium fluoride in the increasing order of their covalent character. This is a direct question. Whenever we are looking on to cations and anions, it is clear that cations are common and anions are different. With increase in size of the anion, their polarizability and the rate of polarization will be high. So, sodium iodide is having more covalent character and the least covalent character is associated with the sodium fluoride. I minus is largest and more polarizable, while F minus is the smallest. This is an MCQ based on the concept we learned. Which of the following factors increases the covalent character in an ionic bond? These are your options, and based on careful analysis of the option, you can arrive at the final result that your option will be option B, that is small cation and large anion. Moving on to another MCQ. Which of the following compounds has most covalent character? These are the options. It includes sodium chloride, magnesium chloride, aluminum chloride and potassium chloride. This is your answer. Answer is option C, that is nothing but aluminum chloride. The answer aluminum chloride is because of the fact that aluminum 3 plus has the highest charge and smallest size, which increase the polarization and hence covalent character. So, higher degree of polarization is observed in aluminum chloride. It is associated with the highest covalent character among all these options. Now, another MCQ. Which of the following anions is most polarizable? These are 4 anions: F minus, Cl minus, Br minus and I minus. Polarizability is directly proportional to size of the anion. You have to keep that point in your mind. Based on that reasoning, you can arrive at the final answer as option D, that is I minus. Larger anions are more polarizable because their outer electrons are less tightly held to the nucleus. Now, which of the following cations has highest polarizing power? These are 4 cations. Na plus, K plus, Al3 plus and Mg2 plus are there. The answer is aluminum 3 plus because high charge and small size results in stronger polarizing power to aluminum 3 plus. Now, this is the last MCQ of this module. Which of the following has the least ionic character? NaCl, LiF, AgCl and CSI are the options. On careful analysis and based on Fajan's rules, you can arrive at the answer as option C, that is silver chloride. Silver salts have more covalent character due to pseudo-noble gas configuration of Ag+. That all about the present module. Have a nice reading experience. Thank you.